Hello, and welcome to the Future AI Society YouTube channel, where we're adding common sense to artificial intelligence. Today, we're diving into an incredible tool in computer vision, the Hough transform algorithm. Let's get started. At the heart of computer vision lies the ability to detect shapes from images, and the Hough transform is a powerful technique that helps us do just that. But what makes it stand out? Let's find out. In this video, I'll describe our Hough algorithm implementation, some enhancements we needed, and how it fits into the Future AI Society's overall target of adding common sense to artificial intelligence. All the code is available online at the Future AI Society repository on GitHub as part of our BrainSimIII project. Let me know what you think, leave comments and questions, and download the code and improve it. But first, be sure to like and subscribe to this channel, then join the Future AI Society to be updated on all our ongoing development. Common sense isn't just about knowledge. It requires understanding our three-dimensional world and how objects interact within it. This concept is crucial for developing AI that truly understands the world around us. You don't understand the world around you because you've scoured the web and read about it. You understand the world because you've interacted with it and explored it with multiple senses. The Future AI Society has taken a giant leap with the BrainSimIII project, creating the Universal Knowledge Store, or UKS. It stores a web of information that mimics our own brain's way of storing multisensory experiences. In this optical illusion, your mind sees a square. Even though no square exists, only 4 disks with bits missing. This demonstrates how our brains have a fascinating way of recognizing shapes by focusing on corners. As an aside, you can look at any optical illusion as a clue about how your brain processes visual information. Storing corners allows us to recognize shapes regardless of their orientation, size, or position. Because your brain stores shapes as only the corners and the relative distances between them, your brain needs much less storage than if it needed to store every possible size or position, a huge reduction in the amount of memory your brain needs. The Hough algorithm plays an important role in recognizing shapes because it can locate lines in an image, and these lines can be used to detect corners at the intersections of the lines. Here you can see the entire process in action. From an input image, detect the boundaries. Use the Hough algorithm to locate lines in these boundaries. Convert these lines to segments. Find the corners at the intersections of segments. Put the corners into the UKS for downstream shape and object recognition, which I'll cover in a subsequent video. Before diving into the Hough transform, it's crucial to start with boundary points rather than the raw image. This demonstration includes a simple yet effective boundary finder to set the stage for the Hough transform. At its core, the Hough transform lets computers find straight lines in an array of boundary pixels. The Hough algorithm considers all the possible lines going through every boundary pixel and creates a cluster of lines which might possibly exist in the image. In this simple image, the possible lines are shown with more likely lines being progressively lighter. Once the lines are created, the most likely lines can be considered and reduced to line segments. Then intersections between the line segments can be detected as corners, which are put into the UKS. You may recall from high school that a line can be expressed in the form y equals mx plus b, where m is the slope of the line and b is its intercept with the y-axis. The key is that you can define a line in terms of just 2 parameters. This means you could define a 2-dimensional array with each entry corresponding to a possible line like this, where a single entry represents a line. We could let the array's value represent the likelihood that such a line exists in the image. If you are mathematically inclined, you can consider this 2-dimensional array as representing a 2D space, and thus the image boundaries have been transformed into a new representation, which is why the Hough algorithm is usually considered to be a transform. In this case, the 2 bright spots in the transformed result represent the 2 lines which were found in the input image. So, we can look at every point in the input array and ask if it is a boundary point. If it is, we can consider every line which might possibly go through that point and calculate the 2 parameters of those lines. We can treat these 2 parameters as the indices into our array, which we'll call the accumulator array. Think of it as a 2D scoreboard. Every time we find a line that might pass through a boundary point, we give that entry an additional vote. After all votes are in, we check the scoreboard. The array positions with the most votes represent where we'll likely find our lines. Now, I'd like to add 2 wrinkles which make the Hough transform really cool. First, you may have considered that there are an infinite number of lines which might go through any single point in space. But there's great news for computers because since our images are digital and are composed of pixels, there are a limited number of lines which might possibly be represented. Second, and this is really cool if not a bit confusing, if we describe a line as y equals mx plus b, as the line becomes vertical, the slope tends to infinity and the intercept is undefined. As you know, infinity doesn't play well with other numbers, and it would imply that we'd need an infinite array to store our votes. So let's use another way of defining the line, by its angle, as opposed to slope, which we'll call theta, and its distance from the origin, which we'll call rho. Instead of being defined by m and b, any line can be defined in terms of rho and theta. Now, we can create the accumulator array for all possible values of rho and theta. Rho is limited to values within plus or minus the diagonal size of the image, and theta is limited between 0 and 180 degrees with a step size defined at our discretion. In this example, our image size is 100 by 100, the diagonal is 141, so the accumulator array is 282 by 180. In code, the entire Hough algorithm looks like this. Pretty simple. We step through every point in the boundary array by x and y. If there is a boundary at that point, we step through all possible lines at that point and add votes to the accumulator array. At this point, we have an array of possible lines and the number of votes accumulated by each, which represents the number of points we found as boundaries on each individual line. We'll see that there are clusters of lines because if we have a group of boundary pixels in a row, rounding issues mean that there will be multiple possible lines through them. So from our triangle, the Hough transform finds a suite of lines. But the line with the most votes is likely to be the actual line in the image. So we'll handle that with an algorithm to find the local maximums in the accumulator array. This is a bit tricky, so look at the code to see how we've done it. If there's interest, we can make another video with descriptions of more tricks. But the Hough algorithm finds lines and we need segments. For this, we tweaked the Hough algorithm itself, so instead of just counting votes, each entry in the accumulator array is modified to be a list of points. Instead of just incrementing the accumulator entry, we'll add the point to the list like this. The number of points in the list is exactly the same as the vote count was previously. But when we want to find the segments, all the points which contributed to this line are waiting for us to use them to find the segment endpoints. A straightforward algorithm can step through each point list and find the contiguous points which represent a segment. Now, we can use some geometry to find the intersections between the segments which represent the corners we need for the rest of the object recognition process, which we'll cover in a future video. Why didn't we just use OpenCV? While OpenCV is a fantastic resource, we found that creating a tailored solution allowed for greater flexibility and efficiency, all within less than 500 lines of code. If you're fascinated by how AI can learn to see the world, dive into the Future AI Society's GitHub repository. Explore the code, contribute, and be part of this exciting journey. Don't forget to like, share, and subscribe for more tech insights and join the society. Thanks for watching the Future AI Society channel. Stay curious, keep learning, and see you in the next video. And as always, thanks for watching.